Hello, we're just going to do a quick review for Module 4 to prepare you for either the test or your DBA. So we're going to go ahead and get started. So Lesson 4.01 largely deals with chemical versus physical changes. Now the basic difference between the two is a physical change is caused by a change in phase states, for instance, a liquid going to a gas. It could also mean that you are cutting or ripping something up. But the big thing is that at the end of the reaction, you still basically have the exact same thing at the end. So it involves, for instance, some examples like your aluminum foil being cut in half. It includes butter being melted in the microwave. All right, now chemical changes, vice versa, a chemical reaction is actually occurring. So basically, at the end of a chemical change, you can't get back what you started with. And some examples of chemical changes include things like milk going sour, jewelry varnishing. It could be something, if we go back to a food example, that if you burn a marshmallow, for instance, the combustion of that marshmallow is going to become brown. And color changes are very indicative of chemical changes. But the big thing is that you can't get the original ingredients back. So that's the big difference between chemical and physical changes. Now, lesson 4.02 deals with a very important topic of balancing equations. So you want to make sure that you can explain why it is important to always balance equations. And of course, that has to deal with observing and preserving the law of conservation of mass. Remember that matter and energy can neither be created nor destroyed. They can only change form. So we have to maintain that, and that's why it's important to balance chemical equations. We also need to make sure that we can describe what coefficients represent and how they relate to the law of conservation of mass. Third, we want to be able to use those coefficients to balance a variety of chemical equations. So remember what a coefficient is. If I have an oxygen, all right, I'm going to have a subscript of 2. And if I'm going to put a coefficient is going to be the big number that is in front. So here's our coefficient, and here is our subscript. Notice the relative location of each one of these. So, an important thing that you need to know when balancing equations is that we are only allowed to change the coefficients in front of a formula and not the subscripts within the formulas. Now, the reason that is so important is because if you were to change a subscript, it will no longer be the same compound. So, for instance, let's say we have water, okay? So everybody knows water is H2O, all right? If I suddenly was to change a subscript and make it H4O, that is no longer water. So the proper way to add more hydrogens onto this if we need to is we're going to put a subscript in front. So now I've changed the number of hydrogens without actually altering the identity of our compound. So that's an important point to keep in mind. Lesson 4.03 deals with the identification and working with double and single replacement reactions. So for this lesson, we want to not just identify, but we'll actually work with these two different types of reactions. We want to be able to predict the products of double and single replacement reactions. And we're also going to be using an activity series. By the way, you should have your activity series in your notes previously. If you have not put it in your notes yet, this would be a good time before you take your DBA to make sure you have it somewhere in your notes, because your teacher could be asking you an activity series question as part of that. So lastly, with this lesson, we're identifying some of the common properties of single and double replacement reactions. So now, in dealing with the activity series, we need to note, especially in a single replacement reaction, a reaction will occur if the individual element is more reactive, higher on the activity list series, for instance, than the element it is trying to replace. All right. So basically, if you start at the top and you are working your way down, the reaction will occur. If you try to start at the bottom and work your way up, the reaction will not occur. So for instance, if we look at the bottom reaction here for aluminum, we can see that if we look at aluminum on our activity series here, aluminum falls right here. All right, it is trying to replace potassium, which is much higher on the list. So since we're going from here up, that reaction will not actually take place. But let's say, for instance, we are working with magnesium and cobalt. Magnesium is here on our list. Cobalt is lower on the list, and since we're working our way down, the reaction will actually take place here. So again, make sure that this activity series is somewhere in your notes. You don't know if your teacher is going to be asking you a question about it, and you may also need it for your tests. So make sure that you've written that down. Now, what do double and single replacement reactions actually look like? All right, so a double replacement reaction is as follows. The name kind of gives it away. You have two binary compounds, in other words, compounds that have two parts to them, and they are going to be flip-flopping with each other. So A and B are going to swap partners. So if we look at our first example here for double replacement reaction, here's the first part of these. So for this reaction, if it's going to occur, silver is going to be taking the place of sodium. And what we see here is they have indeed switched partners. Our silver is now sitting with the chlorine, and our sodium is now sitting with our nitrate. So the basics behind it is two binary compounds, and you should see a double switch. Now, single replacement look a little bit similar to this, but they have one big key difference. You will see an element that is sitting all by its lonesome in a single replacement reaction. So notice here, A is not going to be with anything else. It is a lonely element. All right, sometimes it's paired up with something else, like in this case, it's binary, but you notice that it's not bonded to another element. So if you see a lonely element sitting by itself, and then replacing something within a binary compound, that is single replacement. But at the end of this reaction, you will still have another element that will end up being lonely instead. It'll just be a different one. So in this case, use the words to help you out. Double replacement, we're replacing something twice. Single replacement, we're replacing something just one time. And remember, it's going to have something that is going to end up being lonely here at the end. So look for lonely elements. Now, lesson 4.04 deals with synthesis and decomposition. So same sort of idea with this, just obviously different types of chemical reactions for this. So the basic premise behind this is you are still predicting your products. You are identifying synthesis and decomposition, and you're identifying common properties. So here is what a synthesis reaction actually looks like. So synthesis is building something up. So I tell students, consider putting something like bricks in your notes or something like that, so you understand that you're building something up. So synthesis basically starts with two compounds, and at the end, the big thing is that we only have one product at the very end. So we can see here for our first example, we have a sodium and an oxygen, and at the very end, we only have one big product. We don't see anything hanging out here. There are no lonely elements at the end here. So That's the big difference between a synthesis reaction and what might look a little like a single replacement reaction. Remember, no lonely elements means you are probably looking at a synthesis reaction. Now, decomposition is the exact opposite of synthesis. Decomposition, we start with a complicated compound, and it's actually decomposing and breaking up into its component pieces. So remember decomposition. Now it's kind of a gross example, but you'll remember it. Remember what's happening when a body decomposes. The body is very complex, but breaking down into its most basic elements. All right. So same thing goes for a decomposition reaction in chemistry. Start complex, break down into simple elements. But remember, the thing that is complex, there's just one of them. So that's how you differentiate that and what might look like a double replacement reaction. So look at what you're starting with for decomposition reactions. Now, lesson 4.05 deals with one particular reaction, and it also deals with the lab. Don't be hesitant. You really should look at your lab report before studying for the DBA. You may be specifically asked questions about your lab report for lesson 4.05. Combustion has a very characteristic look to it. And it's also big because combustion releases heat and light. So I always tell students, combustion, think of the word campfire, because a campfire and combustion both start with C, and they are both, and a campfire is a combustion reaction. Now, the big thing with combustion reactions is they always will have oxygen as one of the reactants. So you can see here, no matter what. Now think back to our campfire for this. So what happens when you throw water or you throw dirt on a campfire? You take away the oxygen and combustion can no longer occur. All right, so key thing here with that. Now, very important, some combustion reactions can also be synthesis reactions, which is all about what your lab was getting at towards the end. So we actually see this second combustion reaction here. Notice we've got two compounds going and making one. So there are instances where combustion reactions can also be synthesis reactions, but the big overwhelming thing to identify combustion is that O2. The presence of that O2 as a reactant is very important. So anytime you think combustion, think of campfire. Again, remember they share that first letter, and that'll be a handy way to help guide you in the direction of understanding what combustion reactions are. So getting onto a lot of the stuff that students struggle with quite a bit for this is stoichiometry. Now, stoichiometry looks complicated, but it's actually just a series of very basic dimensional analysis things, and it also includes balancing a chemical equation. So we're taking a skill that we learned earlier on in Module 4, all right? We're combining it with some of the skills we've been using throughout the course with dimensional analysis, all right? And we're just basically putting them together. So stoichiometry incorporates these things together and also incorporates something called a mole ratio. Now, a mole ratio is kind of a magical thing. It's kind of like a bridge, because a mole ratio can allow you to convert one kind of mole into another kind of mole. So mole ratios are really great with that. And where in the world do we build a mole ratio from? We grabbed numbers, specifically the coefficients from our balanced chemical equation, and we use that to set up our mole ratio, and then we magically can make one type of mole into another type of mole. And then from then on, you're really just completing dimensional analysis, which you've been doing throughout the course already. So all things you've done previously in the course, we're just adding elements all together as one. So let me show you an example of what this would look like. So here is a stoichiometry problem. So it says how many grams of sodium metal are needed to react completely with 45.6 grams of water. So we have our chemical equation, and first thing